Hey guys, and welcome back. My name is Miss Danielson, and today we're doing an introductory lesson to travel graphs, or distance time graphs. We sometimes call travel graphs distance time graphs because they show distances traveled over some period of time. We graph them by plotting time left to right across the horizontal axis, and distance from some given point is plotted up the vertical axis. Here's an example of a graph which shows a constant speed. It shows that we start our journey at a distance of 0 kilometers at time 0, and we end our journey at a distance of 300 kilometers after 3 hours. One straight line between 2 points indicates a constant speed. The start and end points can be very helpful in working out the speed of that part of the graph, and it could also help us to work out the different times or distances along that line. In this particular example, it should be fairly easy to figure out how many kilometers this object travels in an hour, because we see the time at the bottom here for 1 hour, which leads us up to this point on the line. Now this point on the line is lined up with a distance on the vertical distance axis. It's lined up with 100 kilometers. So that tells us that in 1 hour, the object travels 100 kilometers. Now notice the proportion here. We said that in 3 hours, we could travel 300 kilometers, and in 1 hour, we can travel 100 kilometers. Since 1 hour is 1/3 the amount of time, 100 kilometers is 1/3 the distance that we travel. Again, since this is a fairly simple example to start with, the speed should be pretty easy for us to figure out. If we know that we can travel 100 kilometers in 1 hour, you should know that a speed in kilometers per hour is simply the number of kilometers we can travel in an hour. So in this case, our speed is 100 kilometers per hour. The speed isn't always that obvious, but this speed distance time triangle here will help you to work out the speed when it needs to be calculated. As you can see in the triangle, we've got the distance d at the top and the time t at the bottom. That means to work out the speed, we would simply do distance divided by time. On a graph, the speed is seen in steepness or gradient of the line. If you're familiar with the equations of lines, you might already know that the gradient of a line is calculated by rise over run. That is how high we rise up as we run across. The distance, remember, is the vertical measure, and the time is the horizontal measure. So this relates very clearly back to the formula for the speed being the distance over time. Steeper lines on a graph show faster speeds. So looking at these two lines, can you tell which one's steeper and which one would represent a faster speed? That would be the second one here, because we're traveling a further distance in a shorter amount of time. Here we're taking a much longer time to travel a shorter distance. Faster speeds means more distance in less time. A speed which is represented by a horizontal line simply shows the speed of 0. That's because time is passing, but the distance isn't changing. This cat's not going anywhere. He's completely stopped. Lines on travel graphs may slope upwards or downwards, but that does not indicate an increase or decrease in speed. Upward sloping lines simply show outward journeys. The distance is increasing, while downward sloping lines show return journeys. That means we're returning to our starting point. As we know, time always works forward across our time axis, that is from left to right, while our distances increase as we go up. So on a travel graph like this, as time goes by, our distance from our starting position is increasing. We're going away from home. On this travel graph, however, as time goes by, our distance is decreasing. So this is returning back home. These two green lines are quite interesting because they show the same amount of distance being traveled. And if you look closely, it's the same amount of time that it takes as well. These two green lines show an equal speed. It's simply that one speed is working away from home and the other one is returning back home. Let's have another look at this example. How far is this object traveling in 2 hours now? Again, we can read that directly off of our graph. Our time is down here at the bottom, and here we have 2 hours. So follow that line up. See the point on our travel graph? It's right here. Follow that directly horizontally across to the distance, and we see that in 2 hours, we can travel 200 kilometers. How far does the object travel in 30 minutes? So long as you understand that 30 minutes is half of an hour, you should be able to find 30 minutes on your graph right here and follow that up vertically to the point on the line and follow that horizontally across to see its distance. Now in 30 minutes, we can see that we can travel 50 kilometers. Some people really struggle with scale when there are some values on a graph that aren't labeled. I've labeled each of the hours, but I haven't labeled the minutes in between. So let's have a look at how we can work out the scale of a graph. To work out the scale of a graph when not all of the squares are labeled, we should first count the number of squares between each labeled number. So if I look at my time axis down here, I can see that there are 5, 10 squares to get to 20. Then let's find the value of each of these squares. If it takes 10 squares to get to 20, 20 is being split up or divided into 10. So each square is worth 20 divided by 10. That's 2 seconds per square. So the scale can be written now in the form of a ratio. That is the number of squares, which represents their values. I could say that 10 squares represent 20 seconds, or I can simplify that to simply be 1 square represents 2 seconds. Now I can look at my graph and say, okay, so this must be 2 seconds, 4 seconds, 6 seconds, 8 seconds, 10 seconds, 12, 14, 16, 18, and 20. Once I get to 20 on the 10th square, I know that I followed the correct scale. Take a minute now to copy down those steps for how to work out a scale. Now let's look at the scale of this graph. We see that it takes 4 squares to make up an hour. 1, 2, 3, 4. An hour is 60 minutes. So if we want to work out how many minutes each square is worth, we'll simply do 60 divided by 4 because it takes 4 squares to make up those 60 minutes. 60 divided by 4 is 15 minutes. That means each square is worth 15 minutes. So let's write that scale as a ratio. 1 square is therefore equal to 15 minutes. And if that helps you, you can label your axes now. Now that we've labeled every single square on the time axis, working out the distance that this object travels in 15 minutes should be simple, right? 15 minutes on the time axis is right here. I'll follow that up to the point on the travel graph, and I'll follow that point across horizontally to figure out the distance. But what is this distance? If you can't actually see the value you're looking for on the travel graph, you should use values that you can clearly read from the graph to help work out those values which are not so clear. If I know that I can travel 50 kilometers in 30 minutes, and 15 minutes is half the amount of time, well then I could simply half the distance. 30 divided by 2 gives me 15, and 50 kilometers divided by 2 gives me 25 kilometers. As you can see, these examples are starting to get a bit more challenging. What about the distance we could travel in 4 hours and 30 minutes? Now, 4 hours and 30 minutes, that's 4.5 hours. And that doesn't fit on my graph. My graph only goes up to 3 hours. When looking for values which are not on your travel graph, you'll need to calculate them, like we just did. One way we can do that is by using equivalent ratios in calculations. That's by using a relationship between a pair of known values to find a value which pairs up with the value we're asked to find. For example, when we were looking at scales, I could see that the number of squares is somehow related to their value. 10 squares represent 40 minutes, so 1 square should be somewhat related to this proportion. I have to think what I did to the 10 squares to get down to 1 square. I divided by 10. So I'll do the same thing to the 40 minutes. If it's 1/10 of the number of squares, it should be 1/10 of the amount of minutes. So 40 divided by 10, that's 4 minutes. Each square is worth 4 minutes. And again, like we did before, we could check that by counting by 4s. 4, 8, 12, 16, 20, 24, 28, 32, 36, 40. Now, if we want to apply that to distance and times, Zara can cycle 18 kilometers in 1 hour. How far could she cycle in 3 hours? Again, we could set up a ratio that shows the relationship between time and distance. In 1 hour, we can travel 18 kilometers. 3 hours is 3 times that amount of time. So we should be able to travel 3 times that distance. So 18 times 3, that's 54 kilometers. So in 3 hours' time, Zara could cycle 54 kilometers. Now let's try applying that method to this question. 4 hours and 30 minutes is off my graph, but I can use a value I see on this graph. For example, I know that in 1 hour, we can travel 100 kilometers. So I'll set up my ratio of time to distance, where the time is 1 hour, the distance is 100 kilometers. When the time is 4 hours and 30 minutes, well, that's 4.5 hours. That's 4.5 times the amount of time. Then we should travel 4.5 times the amount of distance. 100 kilometers times 4.5 is 450 kilometers. Alternately, we could have also used the speed distance time calculations, or the SDT triangle. Even if you're comfortable working with ratios, it's important that you learn these formulas because they can be applied to any type of speed distance time calculation. Again, here's our speed distance time triangle, and as we've seen before, we calculate the speed by doing the distance divided by the time because the distance is on top. But if we want to work out the time, again, we would have the distance on top, but it's on top of the speed. So we would do distance divided by speed. The only tricky one is when we want to work out the distance because speed and time are next to each other. So there you need to remember that when these two variables are next to each other, we multiply them. So distance is equal to speed times time. So now that we've worked out our answer using ratios, we could also compare our answers if we use the speed distance time calculations. And I'm sure they'll be the same thing. So let's look at the given information. We know that the speed of this graph was 100 kilometers per hour. We worked that out in the beginning, and you can see here that in 1 hour, we travel 100 kilometers. We also know that the time that we're looking for is 4.5 hours. Now that's off our graph, so we can't see it on the graph, but using our calculations with the speed and the time, looking at my speed distance time triangle, speed is next to time, so to work out the distance, I do speed times time. That's going to be 100 times 4.5, which is 450 kilometers. So whether you work this out through ratios and proportion or through the speed distance time calculations, we get the same answer. It's 450 kilometers. Next, let's clear up a bit of vocabulary that I know a lot of my students confuse. When I say how long does the object take to travel 250 kilometers, I hope you realize that how long is a reference to how much time. How far is a reference to distance, so please don't get those confused. Obviously, we've got the distance here, it's 250 kilometers, and I'm trying to figure out how much time it would take to travel 250 kilometers. For this particular question, we can again just read it directly off the graph, because 250 kilometers is up here on the distance axis, and I'll follow that across till I see my point on the travel graph, and I'll follow that point downwards to my time axis, and I see it's here between 2 hours and 3 hours. Following that scale that we talked about before, I know that there's 4 squares between each hour. So each square is worth 1/4 of an hour, which is 15 minutes. So that's 2 hours and 15 minutes, 2 hours and 30 minutes. It's going to take 2 hours and 30 minutes to travel 250 kilometers. How long would it take to travel 500 kilometers? Now again, that's another value that's off my graph. So I'm going to have to calculate. Using ratios and proportions, using values that I already know, I know that a distance of 250 kilometers can be traveled in 2.5 hours. 500 kilometers is simply 2 times 250 kilometers. So that would take twice the amount of time. 2.5 hours times 2 is 5 hours. Alternately, if I use my speed distance time calculations, I know that the speed is 100 kilometers per hour. Remember, we worked that out at the beginning, and we can see that here. In 1 hour, we travel 100 kilometers. Now, if we're trying to work out the time it would take to travel a distance of 500 kilometers, the other given information is the distance. I know that d is equal to 500. So in my speed distance time calculation, I would do distance divided by speed, which is 500 divided by 100, which is 5 hours. So either way, I know that it will take 5 hours to travel 500 kilometers. Take a minute to revise your speed distance time formulas now. Make sure you've written those down because we're just about to get into the practice exercise. In this practice exercise, you'll look at these 5 different travel graphs. And for each of them, you're going to need to work out the scale for both the time axis and the distance axis. This is the first thing you should do anyways, because you can't work out the values on the graph if you don't know what scale we're using. Then you're going to work out the speed represented by the travel graph. Notice that these are all straight lines, so they all represent a constant speed. Then, for part C, you will work out how far we could travel in a minute on each of these travel graphs. And for part D, you'll figure out how long it would take to travel 18 meters, according to each of these travel graphs. Let's have a closer look at each of these questions. Here's question 1. Feel free to hit pause so you can work out your answers. Now question 2. Question 3. Question 4. And question 5. Now I hope you've taken your time to hit pause and work those answers out for yourself, because here come your answers. For question 1, the time scale shows 10 squares make up 10 seconds, so each square is worth 1 second. The distance scale shows 5 squares make up 5 meters, so 1 square is worth 1 meter. The speed I can work out from any point along the line. However, this point is not very clear. It looks like it takes 2 seconds to travel 1 meter, but is that true? Here are some other points along that line. And it's always best to choose a reference point further along the line because it's very easy to misread values that are very close to the beginning of the line. So let's work out our speed given these 3 coordinates. Remember, speed is distance divided by time. If this point was right, we'd simply do 1 meter divided by 2 seconds. And that gives us a speed of 0.5 meters per second. But this point here shows that I would travel 6 meters in 10 seconds. 6 divided by 10 is a speed of 0.6 meters per second. And our last point here shows that we can travel 12 meters in 20 seconds. Distance divided by time, 12 divided by 20, gives us a speed of 0.6 meters per second. So it looks like our first point was wrong. Don't choose the first point you see on the line. It's much better to choose the points further along on the line. For question C, the distance we could travel in 1 minute, well, that's off my graph. However, I know I can travel 6 meters in 10 seconds or 12 meters in 20 seconds. So 1 minute, which is 60 seconds, would simply be 6 times 10 seconds, so 6 times 6, or 3 times 20 seconds, so 12 times 3. In either case, 6 times 6 is 36, or 12 times 3 is also 36. We could travel 36 meters in 1 minute. And the amount of time it takes to travel 18 meters, again, that's off my scale. My scale only reaches up to 12 meters. But I do know that in 10 seconds, I can travel 6 meters. That's here. And if I can travel 6 meters in 10 seconds, 18 meters is 3 times that distance. 3 times that distance, 3 times that time. 10 seconds times 3 is 30 seconds. For question 2, the time scale shows 1 square for every 2 seconds because it took 10 squares to make 20 seconds. The distance scale shows 1 square for every 4 meters because it took 5 squares to make 20 meters. The speed I can find by looking at either one of these 2 points. I can travel 16 meters in 20 seconds, or I can travel 32 meters in 40 seconds. Speed is calculated as distance divided by time, so I could either do 16 divided by 20, which is 0.8 meters per second, or I can do 32 divided by 40, which is also 0.8 meters per second. The distance I can travel in a minute, again, I need to calculate because it's off my scale, but as I know how far I can travel in 20 seconds, I simply multiply that by 3 to get 60 seconds. So I could multiply my distance by 3 and I get 48 meters. The time it takes to travel 18 meters, well, that's actually on my graph. If this is 20 meters and each of these squares is worth 4 meters, 18 meters would be right in the middle of this square. So right about here. And as these squares are each worth 2 seconds, 20 seconds plus 2, that should be about 22 seconds, right? But I'm not so sure. So I'm going to try calculating this. I know that the speed is 0.8 meters per second and the distance is 18 meters. To work at the time, I'll do distance divided by speed. So distance of 18 divided by speed of 0.8. And that's 22.5 seconds. So I'm glad I didn't just trust my coordinate here because I really can't see for sure how many seconds that is. If you're not sure about the coordinate, it's always best to calculate. For question 3, our time scale shows 1 square represents 4 seconds because it takes 10 squares to make 40 seconds. Our distance scale shows 1 square represents 1 meter because it took 5 squares to make 5 meters. The speed I can work out from either this point or that point. That's 40 seconds for 2 meters or 80 seconds for 4 meters. Speed is distance divided by time, so I can either do 2 divided by 40 or I could do 4 divided by 80. In both cases, that gives me a speed of 0.05 meters per second. The distance we could travel in a minute, well, I could read that off my graph, but am I sure it's going to be very accurate? 60 seconds is exactly halfway between 40 and 80. It's right here on this line. And I read that as being 3 meters. Each square is worth 1 meter. Am I sure it's exactly 3 meters? Well, the distance is exactly in between 4 meters and 2 meters. So that's got to be my answer. Next, how much time will it take to travel 18 meters? Well, that's way off my scale. So let's use some values we know. I know that we can travel 2 meters in 40 seconds. 18 meters is simply 9 times 2 meters. So 2 times 9 is 18. It would take 360 seconds. Alternately, I could use my speed distance time calculations. I know that my speed is 0.05 and the distance is 18 meters. So I'd simply do 18 divided by 0.05. That gives me, again, 360 seconds. Or, since 360 seconds is more than a minute, there's 60 seconds per minute. 360 divided by 60 is 6. For question 4, our time scale shows 1 square represents 2.5 seconds because it takes 10 squares to make 25 seconds. Our distance scale shows 1 square represents 2 meters because it took 5 squares to make 10 meters. The speed I can work out from either of these 2 points. Either way, speed is distance divided by time, so 10 divided by 25 or 20 divided by 50, and in both cases that gives me a speed of 0.4 meters per second. The distance I could travel in a minute is off my scale, but using values that I've got, I could see that 30 seconds would be 12 meters. 1 minute is simply 60 seconds. That's twice 30 seconds. So the distance I could travel would be twice 12. 12 times 2 is 24. I can also calculate that by the speed distance time calculation. My speed is 0.4. My time is 60 seconds. So 0.4 times 60 is 24 meters. The time it would take to travel 18 meters is on my graph. It's right here. It would be 45 seconds according to this graph. 18 meters is 4 squares above 10 meters since each square is worth 2 meters. 10, 12, 14, 16, 18. And that seems to be 2 squares before 50 seconds. Each square is worth 2.5 seconds, so 2 squares before 50 would be worth 5. So that's 45 seconds. Alternately, I can use my speed, distance, time calculations if I don't trust that point. The distance is 18. The speed is 0.4. 18 divided by 0.4 is 45 seconds. So my coordinate was correct, but if I'm not sure, I should always calculate to check. For question 5, the time scale shows that 1 square represents 10 seconds, because it takes 10 squares to make 100. The distance scale shows 1 square is worth 1 meter, because it took 5 squares to make 5 meters. The speed I can work out from these 2 points here. Either way, speed is distance divided by time, so either 4 divided by 100 or 8 divided by 200. Both give me a speed of 0.04 meters per second. The distance we can travel in a minute, we should be able to read off our graph. 1 minute is 60 seconds. If each square is worth 10, that's 10, 20, 30, 40, 50, 60 seconds right here. Now, how many meters is that? That's a bit difficult to read. So let's calculate it. I know the speed is 0.04. I know the time is 1 minute, which is 60 seconds. 0.04 times 60 gives me 2.4 meters. Now looking at that coordinate, I didn't trust it. I couldn't read it exactly. It looks like it's about 2.5, maybe a little bit less. So it is 2.4 meters. The time it takes to travel 18 meters, again, is off my graph. So let's calculate it. I know that I can travel 4 meters in 100 seconds. 18 is simply 4 times 4.5. So multiplying that by 4.5, 100 seconds times 4.5 is 450 seconds. Alternately, using my speed, distance, time calculation, I know that the speed is 0.04 and my distance is 18 meters. 18 divided by 0.04 is 450 seconds. Now that's way more than a minute. How many 60s go into 450? Well, 7 times 60 is 420, so that is 7 minutes and 30 seconds left over. So how did you do? I hope you found this lesson helpful and it gave you a good introduction to not just travel graphs, but also ratios and speed, distance, time calculations. Make sure you keep practicing both of those skills because both will be very valuable to you in the future. Till next time, keep practicing and have fun.